With a question, what's the J vector? I introduced that in the very first class, so we talked about it. Okay. Ideally, you would keep that in front of your mind. And I got, first thing I got was conductivity. Well, it's directly relevant. Okay. And then somebody said current density. Well, that's exactly what J is. Current density, which is current per unit cross-sectional area. Okay. So, there's some consciousness there. And understandably, you've been focused on other aspects of the problem sets and so the lab projects I've had you working on and so forth. Okay. So wasn't bad. Uh, Probably better than I'd usually get from a class. It wasn't focused enough to really have a handle on it. And I'm just saying that because you really want to think in terms of the J vector. I also asked what's Ohm's law, and somebody told me current, resistance, and voltage. And well, that's a limited application of Ohm's law. But this is Ohm's law. Okay? Electric field, conductivity, current density. I guess I'll write that out. The V equals IR thing follows. That's the Ohm's law most people learn. That's Ohm's law. It's restricted to currents and wires and stuff. Okay? This follows immediately in a way that you'll discover when you do the second introductory problem set, which I expect you to have well under control by Wednesday. Okay? Only 6 problem, but everything comes back to this. Okay? Resistivity. Along with a couple of other things, gives you resistance. That's the R in this version of Ohm's law. I is your total current. J is current density. How do you get total current from current density in wires? Okay. You want to put all that together. So I'm not going to tell you about it now. I think you can put it together. We'll discuss it next time to make sure. Okay. All right. Okay. Well, we went and looked at the circuit that we observed in lab last time. And it consisted of a thin wire, which I've got in blue here. Color-coding it. About 60 centimeters long. That's actually a loop. In other words, we essentially have 2 wires here. Okay. 32 gauge. And this wire is 20 gauge. Moderate conductivity, they're nichrome. Now, based on Ohm's law in the form J equals sigma E, tell me if your data make any sense. When I said really thick wire here, I'm going to change that to just say thicker wire. High conductivity. You have data. You have voltage. You have current. Tell me if this makes sense in terms of this. If you want to find resistance, don't use a formula for resistance. Use the J vector and figure out what the resistance would be. You're going to learn what you need to put that together with that problem set assignment. You can also read your book. You can use AI. I heard a great quote that I'll quote for you as soon as you finish writing. I didn't make the quote, which is not quite precise, but I thought it's one of the best summaries of what AI can do for you. It's Mark Cuban. Most person know who he is because I think he was on some stupid show. Okay, which I've never watched. So there, seeing the guy, I know kind of what he looks like because I see his pictures sometimes. I've never heard his name pronounced. It looked like it was Cuban, and I guess it is. Mark Cuban said something to the effect, you can use AI to learn everything, or you can use it to learn nothing. That's kind of boiled down. It's a little longer quote than that. It's worth looking up because I really like the way he said it. Okay, so I think you all understand the difference, because you seem to be learning things. Okay. So when I say figure this out, you got the introductory problem sets, which should be enough, theoretically. You've got your book, which is a very good book. You've got AI. You've got YouTube videos. You got videos that I've made. Okay. You got videos that intelligent people have made. Okay. You got some slick videos, and mine aren't intentionally. And among other things, I don't have time to make 10 hours of slick video. So you can use what I've told you. You can put everything together and totally understand what was going on here in terms of Ohm's law of the J vector. Okay. You get Ohm's law in this form as well, and you should understand how this connects to this, but use this. Then figure out why it's this. Fair enough? Okay. That's a task. You should be able to get that done in 2 days. Only 6 problems in the introductory problem set. If you run into stumbling blocks, we'll talk about it next time. Fair enough? Because I want to talk about really neat stuff now. Okay. Okay. What we've got here is a charge, capital Q, surrounded by a sphere. I know the thing's not quite symmetric, but that's what I did on this try. Okay. And we have an electric field, which is represented by these arrows out here. The dotted lines are just radial lines. Each dotted line could be an R vector. Okay. Now my question is, how many of you think that these electric field vectors all ought to have the same length? And how many think they might have different lengths? Say same, different, or I don't know. Okay. Okay, so let's see. It's 4-1, 3-1. Okay. If you know the radius, which is A, what's the electric field at distance A? Okay, 75% of the class voted incorrectly on this, but some people had reasons, like maybe they're gremlins. Okay, I don't know what said that. Maybe there are other charges, maybe there's something else. Well, that's all extraneous. I didn't say anything about other charges. There's no reason to introduce, right? But yes, if there were other charges, that would change things. So yeah, you might have been thinking some good thoughts there. And that would be true. Also, people weren't sure that that was really at the center, even though I said these are radial lines and they all converge at the center. Yeah, you could have missed that. Okay. If it's not at the center, then it's not uniform. But if it is at the center, then at every point on the surface of the sphere, you're going to have the same magnitude of electric field. Okay. Now, other question. Does the electric field always make the same angle with the surface? If instead of electric field, you imagine a little LED here, it's putting out light in a perfectly uniform, symmetric manner, then in the first place, the light is going to go through every point of the surface at a perpendicular. Just like the electric field is doing here, right? If you got 2 watts of light here, you're going to have 2 watts of light shining through the surface. Matter of fact, you'd have 2 watts of light shining through any surface that surrounds that light, whether it's spherical or elliptical or weird shaped. Okay? That 2 watts is going to get there, like quickly. As soon as you turn the thing on, a second later, shine out 186,000 miles. Okay. So it's more or less instantaneous on any sphere of reasonable size. Okay. Or any surface of reasonable size. But if it's a surface that's not a sphere, or if the LED is not at the center, then it's not penetrating at a perpendicular at every point, right? And it's not uniform. Okay. It's different at different points. If instead of here, it's here, then at this point, you're going to have more light than this point. Okay. Now, analogy with light isn't a perfect analogy, but you can just kind of think of the electric field as shining out or shining in if it's a negative charge. Okay. Penetrating the sphere always at a perpendicular. If you want to do the light, find the intensity of the light on the surface, you would divide the 2 watts by the area of the sphere. Number of watts per unit area tells you how intense the light is. Does that make sense? Okay. The electric field tells you how intense the electric field is. If you multiply the electric field by the surface area of the sphere, That gives you something analogous to the total of 2 watts, okay? So the area of the sphere times electric field is the electric flux. You also have magnetic flux and other kinds of light flux, okay? Heavy flux, opposed to light flux. That makes sense? If you've had multivariable calculus, which a couple of you have, and some of you are taking it now, flux is going to come up real fast, okay? So your electric field's a flux divided by the area. Well, can you tell me what you get if you multiply the electric field, KQ over, I said KQ over R squared. Somebody else said KQ over R squared, and I corrected you. It's A squared, right? KQ over A squared times the surface area. What's the surface area of a sphere? How many of you know what the surface area of a sphere is? Okay, no, I'm not getting on people or anything, but I commented. Nobody seemed to know what the surface area of a sphere was, which is typical. Okay. I said that I have never, since the age of 12, not known the surface area and volume of a sphere. I'm pretty smart, like arguably the smartest person that graduated from my high school, but there are 3 other people who could probably make the same claim that I scored higher in tests than I ever did. Okay, marginally higher, but significant. And on the other hand, Mary Jo Pizzino went into secretarial science, and she could have nailed me to the wall as far as smarts go. Okay, so I'm kind of smart, but not super smart. Okay, at least 30 other people in high school that graduated 250 or so knew that just as well as I did. Okay, it's not the good old days. I'm not a boomer telling you how things were then. I'm telling you that right now, everybody in any educational system that's half decent, including some in this country, but it's a minority, but including almost all in many other countries, know these things, giving them much more power to think. If you don't know these things and have to keep looking them up and remember them only short term, you will be less equipped to function. I said, y'all are going to end up with Virginia Tech and you're going to end up with a good education. Okay? But just be aware that there are some really basic things that you should always know just to live. Okay? Much less to be an engineer. You're going to be a good engineer. Okay. So, and caution. Also, what I thought was really neat was my first year calculus when I learned how to do the integration and find the area of a sphere and the volume of a sphere. I thought it was really neat. Now, boy, that's a lot simpler than decomposing these things into steradians and all that stuff that you do with solid geometry that I didn't completely understand. Okay, I knew what the formulas were, and I tried to understand. We didn't have really a course in solid geometry, real good course in Plainville. Okay. And that was a little harder to think of. The calculus is really easy. And those are integrals you'd always be able to do in any set of coordinates. Now I'm talking about multivariable calculus. Okay. You don't really learn that in integral calculus, although you do learn to do the calculus to find the area. So, all right, here we have it. Now, the big point I really want to make here is this thing, electric field is flux over the area. But the area times the electric field is the flux. So what is the flux? The area of a sphere is 4 pi r squared, which is just 4 times the area of a circle. So if this represents a sphere, the circle you see on the board has 1/4 the area of the sphere, and you can imagine how that works. Okay. You know, you have to curve this thing up, and you're going to basically on each hemisphere, you're going to have twice this much area. Okay. So it's 4 pi a squared, 4 pi r squared, large 4/3 pi r's. Okay. Things that, along with a couple dozen other formulas that you should have learned in 9th grade, you never forgot. Okay. So you probably ought to look up what those are and think about them every once in a while. They're pretty simple. I think they'll be handy to you. And to that advice, what's the flux? Okay, well, in this case, for this sphere of radius A, field magnitude at the surface is kq over a squared. The flux is the area times the electric field. The area is 4 pi a squared multiplied by kq over a squared, which is 4 pi a q. Now, if I draw another surface, say you got some kind of a warp quadric surface or something with Q right here. What's the flux due to Q through this surface? Well, there are a couple of things. One, the field exits here, it enters here, it exits here, enters here, exits here, right? So you got to take what exits minus what enters, or what enters minus what exits, right? And that gets a little complicated. And fortunately, you don't have to do that. But you know that the net flux out of this thing is 4 pi kq. The net flux is what the net flux is. Any surface surrounding this charge Q, any charge Q, any closed surface that charge is inside of has this much flux. Flux phi sub E due to a charge Q through any surface, not just through a sphere. Now, this is something I could have told you in about 30 seconds. We've spent probably 20 minutes or more developing the idea. Okay? So the reason is I want you to always know this. Always know that you can take a charged cube, put it in the center of a sphere, and find the flux, and that's the flux through any surface due to that. As long as the charge is inside. If the charge is outside, the flux is zero. Because what goes in ends up going out. It's a little more complicated than what I said. You might want to think about it. Okay? I spent a lot of time, of course, this is probably in the electromagnetism course, the sophomore level electromagnetism course. Spent a lot of time trying to set up an integral for a charge that was off-center. An integral that I could actually confirm it. I don't think I was successful in doing that. And you don't need to because multivariable calculus tells you that it has to be. Okay? And we'll see that in multivariable calculus within the next few weeks. It's Gauss's law. Okay. So let's say now instead of a charge Q, I've got miracle, I didn't break something. So if I have the sphere, it's a little better. It's not a bad circle. Probably missed the center. The sacred line. Well, it's my units here are a little bit screwy because I say I have 10 microcoulombs per cubic meter. But then I'm dividing by 1 plus R, and I don't have any units of the 1. And I haven't specified what the units of R would be. Okay? So this is kind of what the calculation would look like. But instead of putting units on this and confusing things, I'll confuse them just by using letters. I'll just use an alpha there. How are you going to calculate the flux? Well, first of all, your maximum density is going to be what? Well, it's going to be when R is 0, right? Okay, so your maximum density is going to be whatever alpha is. By the time you get out here to radius A, it's going to be alpha over 1 plus A. Now you could average alpha with alpha over 1 plus A and get some kind of an approximation, but this silly thing isn't linear. So what you have to do is integrate by shells. You just break this into shells. Take a typical, well, left circle, but take a typical shell. Out. Radius near R sub I star. And I've got a delta R here, or actually, yeah, I'll do that. So how much charge is there in this shell? Hopefully you can read that. It's approximately equal to the area of the sphere that you would have at this distance times the thickness of a thin sphere. Multiply the area of a sphere by the thickness of a thin shell at that distance, and you have its volume. And you multiply the volume by the density. The density is pretty close to the same at every point. And you multiply that by the delta R. The total charge is the integral 0 to A this, which is not a difficult integral. Let U equal 1 plus R, so that R is U minus 1 and R squared is U minus 1 squared. Very easy integral. Not trivial, very easy. 4 pi comes out, alpha comes out. So I'm not going to do the integral for you. You try to understand what I just did. You did volumes by shells in second semester calculus. Okay. And all we're doing is multiplying the volume of a shell by the density to get the amount of charge. You want to ponder that. Okay. I should have a better cylinder than this. Really see through this. Go ahead and jot down whatever notes you need to make. Cube minus x cubed is 0. 0x squared minus 4x squared is what? Our quarter. Yeah, okay. Now pretend this a wire, kind of wire that doesn't use carry high voltage power line. Okay. But we're not going to think of it as a wire. We're just going to think of it as okay, let's just say that we charge this thing up. Okay, here, it's a market charge on it. Okay, now it's charged up. How much charge do I have on it? Oh, probably a couple of picocoulombs. I don't know. Okay. But let's just say I have 4 microcoulombs. Okay. So how many microcoulombs is that per meter? Well, that's about 1.5 meters. Let's say I got 6 microcoulombs on it. So I've got 4 microcoulombs per meter. Fair enough? Okay. Now that's on the surface. We're not talking about conduction. Those are inside and they can't get out because they're attracted to each other. Okay. Defined by electrostatic attraction. If one of them tries to get out, there are several nuclei that are going to pull it back. Okay. Now, if I'm standing right here, or take this point right here, just a little bit above the water. The electric field that I experience at that point could be thought of as being due to several sections of the wire. Okay, so this section here kind of has a radial vector that goes out here and gives me a field like this. That makes sense? You see my point? And from here, I've got a radial vector. I'll just kind of go to the center of each one, but these could be random points within the increments. Okay. Now from here, I've got some charge. And it's further away. So the electric field due to the charge in this increment is going to be a lot less than the field due to the charges in these 2 increments that are closest to the point. Does that make sense? And it's also pointing at a different angle. Now on this side, I've got another point. I could do my radial vector. And it might be like this. Okay. Now, one point I want to make is if I go way out here, remember this is an inverse square force. This point is like 5 times as far from the center as the point that gave me this one, this vector, this very tiny, fairly tiny vector. So it's going to have 1/25 of the length. The vector from here is going to have 1/25 of the length of this vector. It's also going to be nearly horizontal. Okay. If you look at these vectors, you can see that if we're in the middle of this wire or whatever it is, charge line, okay, you can see that anything you've got in this direction, the component, any component of any vector in this direction is going to be canceled by component of a vector in this direction. Okay, just looking at 2 such vectors, we got this one and this one, which means the components are going to be like this and this. And the components over here are going to be like this and this. These two add as well, but they're in opposite directions. These two add, they're in the same directions. You're going to end up with twice as much. Okay. These two are in opposite directions. They're going to add to 0. So everything you have in the horizontal direction is going to add up to 0. the field that you get from here at this point is 1/25th as big as the one represented by this little vector. And it's also almost horizontal. It has very little vertical component. Okay. So it's got to be negligible at some point, within our ability to measure, say. If it's an infinite wire, then you're always close to the middle. If it's a finite wire, then as long as you're not too close to the ends, you're pretty much in the middle. If you get real close to the ends, you don't have anything coming from over here to cancel what's going this way, right? And things get warped. So the electric field of a finite wire is going to kind of look like this. It's fine. It's always straight away from the wire until you get out toward the end, and then it starts doing this. Does that make sense? Of course, same thing on the other side. If take this cylinder, put it around this wire, or whatever it is. It doesn't have to be a wire, but it's something that's charged. Okay, now I don't know if you can see, the things. Okay, there it is, and there it is, and if I hold it here, then I'm in the way. If I duck down and hold it above my head, I don't know if you're going to see it or not. Okay. Point is, there's a finite cylinder here. Watch it go by. There it is. And here's the other end. Here goes the wire. All right. Better be careful I don't poke the screen out of my computer over there. As long as that thing is not near the ends of the wire, then I've got this situation. I've surrounded the wire by a cylinder, and the electric field cuts through that cylinder at every point at a perpendicular. Does that make sense? Electric field comes radially out from the charged line, so it always intersects the surface of the cylinder at a right angle. In that case, length L. A flux is E times I times A times L, which is equal to 4 pi K Q that thing you can't read there is just says enclosed. So you got some length of this charge distribution surrounded by a cylinder of radius A and length L. Okay. Whatever the electric field is, comes out at a perpendicular, so you can simply multiply the electric field by the surface area of the cylinder. Okay, and the surface area is just its circumference. which is two pi a being the radius. I was thinking diameter when I wrote that. Okay. Yeah, two pi times the radius is your circumference. I hope everybody knows that. Okay. And you multiply that by the length and you have the area of the cylinder. And you can understand that very easily by just rolling up a sheet of paper into a cylinder. And imagine cutting the cylinder and it spreads out into a rectangle where this is two pi times the radius, and this is its length. Again, if you don't know that, you really want to know that. You want to be able to visualize that. So throw that away. This allows you to calculate the electric field at distance A. And you get E equals 4 pi K Q enclosed over 2 pi A L. And there's more to it that you're going to see in the introductory problem sets. I think I didn't assign all the problems in the first introductory problem set. I think there were 3 of them toward the end that I didn't assign that address this. So those are also assigned for next time. So just make sure you understand the first and second problem sets. I'll make that explicit on the assignments page.